Hello everyone, my name is Elijah Proctor, and today we're going to be talking about addressing the potential limitations and assumptions of ANOVA and linear models and ensuring the validity of their results. And so we're going to be using this game details dataset, which has multiple NBA games with the player statistics. And we're mainly going to be looking at the points scored and the minutes played for examples today. And so first we're going to load our game dataset, and then we're going to select data for a specific team. So we have our Milwaukee Bucks, San Antonio Spurs, and our New Orleans Pelicans. And then we have our, we're going to basically only select those specific teams and store it in our subset data frame. Then we're going to check for normality using our Shapiro-Wilk test for the teams that we specified. And so we're going to store this normality check or our subset of groups by teams. We're going to store it in our points by team variable, and then we're going to loop through all the items stored in here. We have our team as our key and our points as our value, and we're going to remove anything that is not a number, and we're going to make sure there's at least 3 data points before we perform our Shapiro-Wilk test. We call this Shapiro function for the points, and then this returns our test statistic and our p-value. If the p-value is less than 0.05, then we consider that the points for this team may not be normally distributed. And then we're going to test for equal variances across the teams using Levine's test. But first we got to remove any missing values from the group. And so that's basically if the length of the points is greater than or equal to 3, we're going to add that to the clean points by team variable. And if the length of these two arrays are the same, then we're going to perform our Levine test. And so we're going to test for equality of variances. And so we call Levine, this returns our test statistic and our p-value, and then we just print the results. And if it's if the p-value is less than 0.05, then the variances are not equal across the teams. Then we're going to perform an ANOVA test to see if the points differ by team. So we're going to call our ordinary least squared function. Our points is our independent variable, and our team name is our dependent variable. We pass in our subset data frame and make sure that it's fitted. And then we call our ANOVA LM function with our ANOVA results passed in. And this gives us our ANOVA summary, which we then print out. We have in order to visualize point distribution, we're going to use a box plot for every single team for their points. And then we're going to perform our linear regression analysis. And so first we have to convert the string values to a float for the minutes. So we're going to call this function that I created to do so, and then we're going to drop anything that has a missing time value within the data set for the minutes. And then we're going to prepare our independent and dependent variables for regression. So we have the minutes stored for independent variables, and then our points is our dependent variables. We're going to include a constant term in our regression analysis using our add constant function. And then we're going to check for multicollinearity using VIF, or variance inflation factor. So we're going to create a new data frame for that. We're going to store inside of our variable key, we're going to have our x columns, which is our minutes. And then for every single x value, we're going to basically perform a variance inflation factor function call and store it inside of our VIF key. And then once we do that, we're going to fit the linear regression model. Or first we're going to print out the results, then fit the linear regression model using our ordinary least squared function call. And then we're going to print out the linear model summary to get our regression analysis. Once we do that, we'll plot the residuals to check for homoscedasticity using our residual plot. And then we're going to assess the normality of residuals using our QQ plot. Okay, so now let's quickly go over the results that we have here. So basically, first we had to perform our Shapiro-Wilk test for normality for the points scored by players on three of the teams that we specified. So The test shows that the points data for Milwaukee and New Orleans may not be normally distributed, and this is because the p-values are less than 0.05, and this suggests that there is potential deviations from normality in these groups. And then our San Antonio Spurs here, we found out that normality assumption is not violated because the p-value is greater than 0.05. So here we have our ANOVA summary, and this table shows there's no significant difference in the average point scored across our 3 different teams, as indicated by the p-value of 0.835, which is much greater than 0.05. This suggests that the difference in points between these teams are likely due to be random instead of there being any systematic difference. Here in our regression analysis, we have a model that's fitted to examine the relationship between the minutes and the points scored, and we have a positive coefficient of 0.617, and this means that on average, as the minutes played increases, our points scored also tend to increase. And then we have our residual plots versus the minutes played, and so this actually shows us some potential issues because the residuals don't appear to be evenly spread across the range of minutes played, and this means there's possible heteroscedasticity or a non-constant variance of errors. And then also our QQ plot of residuals shows that the residuals are not normally distributed, with significant deviations from the expected normal distribution, and this is particularly at the tail ends of this data. And so this further shows that the assumptions underlying our linear regression model may not fully be satisfied, and this could affect the validity of the conclusions that our models have. So thank you for listening. That is all.